So here I'm going to clarify the work energy equation um, because there have been some confusion in terms of the potential energy work done by the conservative forces, which is same as the potential energy and vice versa. So generally the work energy equation goes like this. So now notice here that delta E is same as the sum of delta K and delta potential energy, right? Or we can say delta U. So now the forces that can be acting on the system or an object could be conservative forces and non-conservative forces, right? The way this equation is set up is that this portion, the delta U, that takes care of the conservative forces like gravity and spring forces, which are conservative forces, right? And here, when we are looking at W or work done on the system or on the object, we only consider the non-conservative forces, which could include friction or any external force. Right? So this is how we set up the equation. Delta K is the resulting potential, a change in kinetic energy of the system, right? Now, the important thing to note here is that if you are free to take a conservative force and use that on the left hand side. Like here, I can also add spring force. I can also add gravity here on the left hand side of the equation, and these will be the work done by the spring, work done by the gravity, and similarly here it is the work done by friction, and here work done by any external force, right? And we are summing everything up to find the total work done, and that is equal to the change in total energy of the system, which is equal to the kinetic energy and the potential energy changes. However, if you have taken a spring and any conservative force on the left hand side of the equation, then you cannot take it on the right hand side. Then you have to ignore it from the right hand side, right? It's one or the other. In most general cases, we take the potential energy as part of delta U just for simplicity's sake, and then when we are calculating work, we only have to worry about the non-conservative forces and any external forces, right, which are also non-conservative. So in many times the question may ask that what is the work done by the spring or what is the work done by the gravity. In that case, if you want to rely on this equation, then you'll have to simply just use that. Take the work done by spring and work done by gravity on the left hand side, and on the right hand side you are going to ignore those forces in delta U. So let's say if you take both spring and gravity on as part of the work on the left hand side, then your equation simply becomes W is equal to delta K, because delta U is equal to 0, because we have taken both gravity and spring as part of this. So this is including all forces, including conservative. Okay, so this is where you have to be careful that when you are setting up this equation, you are free to use the force either on the left hand side or on the right hand side, but not both, right? And now the sign of the work done is same example, the formula is still the same. It's it depends upon the direction of the force and the displacement. If they're in the same direction, it's positive work. If they're in the opposite direction, it's a negative work, right? So accordingly, when you are adding all the work on the left hand side, WF, W external, WS, gravity, if you're adding all of them, you have to just make sure that you're taking care of the signs and properly adding them. And on the right hand side, delta K is always positive, so that you don't have to worry about it. It's going to be half mv square. The change in delta K, half mv final square minus half mv initial square. Okay. Now let me illustrate this with a couple of very simple examples. So first we're going to take a simple equation of a free fall, a ball falling in free fall. So it's over here at height h, and it falls through a height h, and it comes here, and here its velocity is v final, and here its velocity is, for simplicity's sake, let's say 0, right? So I'm going to first use the formula of W is equal to EF minus EI, and it's going to be both delta K plus delta U, right? I'm just general form that we use mostly, right? So W, if there is no gravity, we are not going to use gravity on the left hand side because we are using gravity on the right hand side, right? So gravity is going to go here. So now if gravity goes on here, if you look at it, there are no other external forces. Ignoring the air resistance, there is no other external force acting on the ball. So that means W is 0 actually, right? So the W work done on the system by all forces is equal to 0 because there are no external forces or conservative, non-conservative. I mean, there are no other non-conservative forces. Conservative force is their gravity, but we are using the delta U for that. So then EI is equal to again 0. Now I'm not using mgh for EI because I'm using gravity on the right hand side. I'm not using gravity. No, sorry, I take that back. I mean, in this case, EI is going to be mgh because we are using potential energy. All right, I misspoke. So we are using potential energy. So EI is going to be mgh, and EF is equal to, the potential energy here is 0, but the object has gained a velocity, so half mvf square. Now putting it all back into the equation, is 0 is equal to EF, which is half mv square minus mgh, or half mvf square equal to mgh, right? So now let's do the same thing using the other way, where we are going to use the work done by gravity, include that on the left hand side. So that means we cannot use the potential energy related to gravity on the right hand side. So in that case, the work done is going to be work done by gravity. There is no other external force, so it's only gravity. So we are only looking at the work done by gravity. Now the displacement and the force, both of them are in the same direction, so it's a positive, and the work done is mgh, force times distance. Now EI in this case is 0 because there is no potential energy here, because we are in gravity. You cannot use that as a potential energy because we are using that on the left hand side as part of work. So there is no potential energy and there is no kinetic energy. We said V equal to 0. If V was there initial, then we will have taken the kinetic energy of that is EI. Now EF is still the same, half mvf square, and obviously there is no potential energy, right? Now if you set it up in the same equation again, then work done is equal to EF minus EI. Then you will say mgh, work done, it's positive, right? So I'm going to use the sign positive, is equal to EF half mvf square minus EI is 0. And if you see this equation and this equation, They are exactly the same, right? So either way, whichever way you do, it will give you the same answer, but you have to be just careful that you cannot use a force, you cannot duplicate it on both sides, on the work side and on the energy side. You can only use it on one side. Okay. Oh. All right. So now, for most practical purposes and in general use cases, we use the first part, the use of potential energy, just because it keeps it simple. If a question asks that what is the work done by spring, what is the work done by gravity, then you will have to resort to this to keep it straightforward, still using the same formula, but able to find the work done by gravity. Now with this, now let me take a spring as an example. A spring example is slightly more complicated, so just pay attention to this, right? So again, the work done by spring, let me change the color of the work done by spring is given by half k and delta x square. That means the amount of change or compression or elongation that happens between point A and B, if that is delta x, then the change in potential energy or in the system in the spring is going to be equal to half k delta x square. Now remember, this formula doesn't tell you the sign of the this potential energy or sign of this work done by the spring force. Just because, just if you look at the formula delta, it's always going to be positive. So we have to determine the sign of the work done by spring by looking at the motion. And again, the same thing, the work done by the spring, the direction of the spring force and the displacement, if they're in the same direction, then it is positive work, and if they're in opposite direction, then it's negative work. So for example, if spring here and we stretch it from here to here by a distance x0, let's say, right? In this case, if you see, the spring force is going to be acting in this direction, F is spring, and the displacement is actually in this direction, right? Equal to x0. So the work done by spring in this case is negative. So it is equal to negative half k, and whatever the change in compression is going to be x0 square, right? And when it is coming back from this position back to its original, like wherever in this direction, in this case you will see the spring force is on the left hand side and the displacement is also left hand side. So in that case, the work done by spring will be positive. Now when it is compressing, when the spring is being compressed, again in this case the work done is going to be negative because spring is pushing the object out. So it's the force is on the right hand side while the displacement is on the left hand side while it is being compressed. So in that case the work done is going to be negative. So very straightforward. Look at the direction, look at the spring force, direction of the spring force, and determine whether the work done is positive or negative. Remember, the formula is not going to tell you the sign of the work done by the spring. After that, now to illustrate this, just like we did for gravity, let's take a simple example. Let's take an object which is actually on a surface with mu of mu k, right? So we're going to just keep just use the kinetic kinetic coefficient of friction, and let's say it is pulled from here to here, and the displacement is x0 as we said previously, right? And there is a friction here as well, and the mass is m, right? So then if we set this equation up is equal to delta E equal to delta K plus delta U. We are going to use the potential energy method because the spring is a conservative force. So we can use the potential energy of the spring So and work done by friction will have to go on the left hand side because it's a non-conservative force. So even if you wanted, you couldn't use it on the right hand side. It has to be left hand side. There is no choice. In case of conservative forces, you have a choice, but in case of non-conservative forces, you don't have a choice, right? So I'm going to start with the work done. Now work done, in this case, the only work done that we have to consider is work done by friction, because spring we are going to take on the right hand side, the other force that is present here on this object. So work done by friction, and by definition is always negative, so it's going to be minus mu mg and the distance of x0, right? So that's fine. So we got the left hand side. On the right hand side, delta k is equal to let me just take a step back actually. So in this problem, obviously, we are pulling it from x to x0, or stretching the spring. Let's say, here this was the natural length at which spring's natural length, right? So somebody is pulling it. So there is an external force F that is acting on this, that acted a constant force F that acted it to pull it from here to here. So now F again is also a non-conservative force, external force, right? So we have to then take that into account when we are calculating force. So we have calculated the force for F. We also have to calculate the force because of the external force F, and that again, that is actually positive. As you can see, the displacement and direction of force are in the same direction, so Fx0. So total work done is Fx0 minus mu mg x0, right? So this takes care of the left hand side. Coming to the right hand side, delta k is equal to, so kf minus ki. Let's say it has some potential, some kinetic energy, some velocity v, and when the object is at this point, so we are going to say half m, and we are going to say v0 square. Let's say velocity is equal to v0 here, half m v0 square. Initial velocity was 0, so delta k is half m v0 square, and it's positive as you can see. Now the delta u part, which is the spring potential energy, now again uf minus ui. Since the spring was at its natural length when initially at the initial point, so the potential energy stored in the spring was 0. Stored in the spring was 0, so ui was equal to 0, right? But now as the spring has been stretched in the final position, it has a potential energy of half k x0 square, because that's how much elongation happened between initial point and the final point. And at the natural length, at the initial point, there was no potential energy stored because the spring was at its natural length, so it is half k x0 square. Now we plug everything back into the equation. So total W is Fx0 minus mu mg x0 is equal to delta k half m v0 square plus delta u, and that is half k x0 square. So now if you look at this equation and try to kind of see the practical implication or what is happening, you will see obviously when the object is at the final point, it has half mv square and half kx square energy in there, that we know, right? But on the left hand side, if you see, Fx0 is work done by the force which is providing it, injecting energy into the system or into the object, right? While friction is negating that work done by the external force. So that's kind of subtracting it or negating part of the work done by the external force, but total they are resulting in this kinetic energy and this potential energy. So if we were on a frictionless surface, same work would have given us more final energy in terms of half mv square and half kx square. We would have reached simply, this would have been higher, if there was no no friction in. Now let's try to do it the other way around. If you use the work done by spring as part of the work or the left hand side of the equation and not on the right? So if you look at this, the only conservative force in the system is the spring. So if we don't use the spring as a conservative force as the potential energy, and instead use it as work being done by that force on the left hand side, then on the right hand side there is no potential energy, right? Delta U is going to be 0, so we can ignore that. Only thing we are then left with is delta K, right? So now so let's first look at the work done by spring, right? Because that's the only thing that we have to do. The rest everything we have already calculated before. So work done by spring, as we have said, is equal to half K and delta x square, which in this case is x0 square. Now we don't know the sign yet, so we have to figure out, we have to calculate the sign. Now I'm going to go back on the screen. So now if you look at it, as the object is being pulled forward from its spring's natural length and then to this point, the force exerted by the spring is on the left hand side, right? Because it's trying to pull it back, and the displacement is on the right hand side. So the work done by spring is obviously negative because the two are in opposite direction. So then we are going to give work done by spring a negative sign. So now rest other work we have already calculated, the work done by the external force and work done by friction, right? So we are going to keep that work total and then just add the work done by friction. So it's going to be, work total is going to become Fx0 minus mu mg x0 minus half kx0 square, because we calculated the work done by spring is negative, right? So let's write it down here. Wt is equal to Fx0 minus mu mg and x0 and then minus half k x0 square. This is the total work done. Now the delta E part is equal to EF minus EI. Now if you look at it, as we said, there is no potential energy. The only thing we have to worry about is delta K, because we have already used spring on the left hand side, right? And delta K is basically half mv square. We have already calculated it over here, right? Delta K, and this is the total, right? So half mv square. So all we have to then do is say half mv0 square, and then we plug everything back into the equation. So Wt is equal to delta E. So Fx0 minus mu mg x0 minus half k x0 square is equal to delta E, which is half mv0 square. Or if you write it slightly differently, just move the half k x square on the right hand side. We can write minus mu mg x0 is equal to half mv0 square half kx0 square. Compare this to what we found earlier. Fx0 minus mu mg x0 half mv square half, exactly same, right? So I'm going to mark this here in green. This final and this final, they are exactly the same. So this means, as I said, you can use the same work energy equation. You have to be just careful how you are treating the conservative forces on the left hand side of the equation or on the right hand side of the equation. Rest everything remains exactly the same. If the question is asking you work done by the spring, you can directly find it. Work done by spring is half k x0 square, and then find the sign. X is obviously the delta x, right, between the initial point and the final point. Work done by gravity is mg and the displacement. Obviously you will again look at the forces, force direction and the displacement direction to find the direction of the sign of the work done, but they all work exactly the same way.